Okay.
And the floor is yours.
Okay, so thank you very much. Let me try to share my slides. So here we go. So hopefully you see them.
Mm-hmm. Yeah.
Okay. And this. Well, so I'm starting now. So first of all, I'd like to thank you, all the organizers for this invitation, and especially Elias for the organization and all the local committee. So I was suggested to talk about to tell you about scalar tensor theories and their application to cosmology and astrophysics. What I'm going to do. So I'm happy to do that, and to present a kind of quick review on this aspect. And also, before starting, I'd like to say that, of course, my work were done in collaboration with many colleagues, mainly David Langlois here in Paris, but also many others here in France and abroad. And I'd like to thank all of them for the collaborations. Okay, so the plan of the talk is the following. I will start in the first part by a review on scalar tensor theories and what we call higher order scalar tensor theories. Then in the second part, I will tell you about this DHOST classification. So those theories, to date, they provide the most general class of physically viable theories, which are scalar tensors, and where the gravitons come with only one extra degree of freedom, so one more degree of freedom, which is a scalar. And I will also discuss the phenomenology of these theories, especially their application to cosmology, and if I have some time also to astrophysics. And I will also come back, because Elias told me to come back to this famous constraint and on this famous constraint on the speed of gravitational waves that has a lot of implication in scalar tensor theories. So I'll try to discuss and to come back to the aspect in the end of the talk. So I start with higher order scalar tensor theories. So very quickly, a brief introduction. So I start with something that is very broad, so brief and broad introduction, but I will tell you my motivations behind the scalar tensor theories. So as you all know, general relativity is a very beautiful theory, not only in the theoretical framework, because it describes gravity in terms of Lorentz geometry, and it is in total agreements with observations that we have today. But we know, as any classical theory in physics, it is an effective theory, and it has its domain of validity. And we know that this theory has to be surclassed or modified at atom scales. So, for instance, it is limited. So, general relativity is limited to describe what happens at the Planck scale, so at the mass, at the Planck mass. And we know that we need a UV completion of the theory to say something. And also, you know that very well that there exists this tension to understand the physics at the cosmological scales, and more particularly the problem of dark energy. We have this acceleration of the expansion of the universe, and we know that this leads to theoretical troubles, which are known as the cosmological constants problems. So there are many reasons to try to modify general relativity. And the idea to modify general relativity is to go beyond what we know, to try to find a new physics. And we want, in fact, to have a framework to test the gravitational interactions at these different scales, so the UV scale and the late time cosmological scales. Because what we want is to propose some deviations to general relativity that we can constrain. So I would like to emphasize that maybe when we modify gravity, we don't really want to find a solution of quantum gravity or a solution to the cosmological constant problem, but what we want really is just to have a new theory that can predict new things, new observations, in order to constrain and to show us a new physics. This is the main message that I want to give you in this introduction. And furthermore, I'd like to show you something. A picture which is quite interesting, because even though general relativity is in total agreement with experiments, what I said at the beginning, In fact, it has been tested in a rather narrow window. So I like very much this picture by Claudia Durham, which illustrates very well this idea. It shows the domain in yellow here where general relativity has been tested. And the domain here, I mean, this domain is defined in the plane where you have the mass of the system in the x-axis, and you have the size of the system here. And we see that the domain where general relativity is tested is very narrow, and there are a lot of possibilities to see deviation from general relativity. So there is a lot of room to expect some modifications as well. And here at the scale of the cosmological scales, we see that, of course, and you know that very well, general relativity has not been tested here yet. So now the question is, how can we modify general relativity? So the point is that general relativity is robust and is unique in some sense. And this unicity of general relativity makes the theory, of course, very beautiful. And this unicity, we can see and understand it very well if we present the very famous Lovelock theorem. So if we assume that space-time is four-dimensional and it comes with the symmetries that we know very well, diffeomorphisms, invariance, if we say that gravity is described in terms of a metric, so a spin-2 field in the language of particle physics, and also that we want the equations of motion to be second order, then there is no other option than Einstein gravity plus the cosmological constant. So this is the only thing that we have if we impose these three natural hypotheses here. So there is no really much room available for alternative theories. And then the idea to modify relativity is to relax one of these hypotheses here. So what I like to do now is to talk about scalar tensor theories, where we relax mainly the hypothesis that that gravity is described in terms of a metric only. So here, what we assume that gravity comes with an external field, a scalar field, phi, which will be responsible for the fifth force if we consider this modification of general relativity as candidates to explain dark energy and the acceleration of the expansion of the universe. So we consider these theories where gravity comes with a field. We call them scalar tensor theories for obvious reasons. So we realize the second hypothesis of the Lovelock theorem, but in addition, we are also going, and I will motivate this a bit later, the fact that the equation, we are relaxing the hypothesis that assume the equation of motions are second order. So now we are going to have also higher order equations of motions for the theory. But I will explain this in a few minutes why. So the motivations, why do we consider this kind of modified theory of gravity? The main motivation is that, of course, adding a scalar in the scenario is clearly the simplest possibility. It is the simplest, but still highly non-trivial and ephemeral-ish. Of course, there are many other interesting possibilities. And for instance, if you add a mass to the graviton, if you have bi-gravity series, you can also have vectors like electromagnetism vectors instead of a scalar, extra dimensions, and so on. You have a lot of possibilities to modify gravity. But again, having a scalar is certainly the simplest possibility. And also, most of these more complex situations, they contain a scalar mold in the theory. So somehow, this scalar tensor theory is a kind of seed to understand maybe more complex situation. The reason why also we consider theories where the equation of motions are not assumed to be second order is the following. In fact, if we look at Einstein-Hilbert action, so the basic action for general relativity, this action is expressed in terms of the Ricci scalar, of course, and Ricci scalar depends on, is a function of the second derivative of the metric. So the idea is that if we want a scalar tensor theory where the metric is somehow playing the same role as the scalar, we expect actions to depend on second derivative of the scalar field as well, just to mimic what is happening with general relativity. And if we introduce second derivative of the scalar in the action, we will get naturally higher order equations. And we're going to see that we can do that in a very precise way, and this will lead to a very rich phenomenology that I will explain a bit later as well. So now what I'm going to do is to present you the construction of scalar tensor theories. We know that the idea of constructing scalar tensor theories is very old. It dates back to Bruns and Dickey in the 60s. But this kind of theories has evolved a lot in the last 20 years. And this is what I'm going to explain now. So now, let me give you, as I said, a brief review on what we know, what is old concerning scalar tensor theories, and what is new. So the first theories that we know very well were due to Bruns-Dickey in the 60s here. And these theories are defined by an action like this, where you have a metric and a scalar field. And here you recognize the Ricci scalar. And the metric is not minimally coupled to the scalar field. So you can have a free function f of phi here. And also you have the dynamics of the scalar field, which is given by this kind of action. And x will play an important role in the following, is the kinetic energy of the scalar field, namely phi dot square. It's just a d mu phi, d nu phi. And so this is the well-known Bruns-Dickey series. And these theories were discovered in the 60s, and in the 2000s, because of the discovery of the acceleration of the universe, we started to reconsider these theories to account them for dark energy. And one possibility was to extend this theory, and instead of considering a Lagrangian for the scalar field, which is linear in the kinetic energy, we can have a function, G2, which is arbitrary functions of phi and x. And these are called K-essence theories. They were studied a lot. I'm not going to explain them and to tell more about this. But one thing, one important physical consequence of considering K-essence theories is that we can have a non-minimal coupling to external fields. So for instance, if you consider external field psi, then you can get this kind of coupling, psi nu with a function of phi. And this leads to a non-minimal, this is a non-minimal coupling. It leads to violation of the equivalence principle that can be severely constrained by observations. But nonetheless, even though this kind of coupling has been studied and constrained a lot, the phenomenology behind these theories is very interesting, especially for inflation and dark energy. So these are kind of classical scalar tensor theories. Then in the early 2000s, also there were these three breakthroughs, the DGP model that was introduced by these three people, Dvali, Gabazadze, and Porati. The context of this scalar tensor theory was those of brain cosmology. I don't want to enter into details. And there is one novelty, what was quite important, is that you see here, you recognize the K-essence theories, but then you have a new term, which was called later the cubic Galilean, and you start adding directly in the action higher order derivative of the scalar field. So this is something which seems to be very few modifications, but it has a lot of very interesting consequences. And this DGP model was in fact really the cornerstone of the new way of seeing and studying scalar tensor theories in the community of cosmology. But there is one thing, is that even though you have higher order terms, derivative of phi in the action, you still have second order equation of motion in this kind of series. So as I said, you have a very interesting late cosmological phenomenology associated to these theories. And for instance, if you consider a very simple example in this family, you can have self-accelerating solutions. So you reproduce the acceleration of the expansion of the universe, and you can fix the new coupling entering in these actions such that you recover the Hubble constant, the Hubble rate today. But what is interesting in these theories is that you have screening mechanisms, which means that you modify gravity at a large scale, but at small scales, at the scale of the solar system, you recover general relativity. And you're happy to have that because we know that general relativity is well tested in the solar system scales. So this means that you modify a large scales and you have a screening, and inside some radius, which is called the Weinstein radius, you recover exactly what we have in general relativity. So this was really, really interesting. And then after that, people started to generalize the construction, and they wanted to see if it was possible to extend the construction of DGP, and this is possible. And this led to the rediscovery. This led to the rediscovery of Horndeski series. And here, this is a part of the Horndeski theory where you have the quiescence term, the cubic Galilean, and terms which are quadratic in the second derivative of the scalar field. And in this action, all these coefficients, G2, G3, G4, they are in fact functions of the scalar field and of the kinetic energy like this. And these are well known under the name of Horndeski. So I've just put here all the references associated to this work. There were a lot of activities around the Horndeski theories and their application to cosmology. And I would like just to summarize a few things. So why Horndeski theories are so interesting? Because they provide self-accelerating solutions without cosmological constants. So we have a new scenario for the acceleration of the expansion of the universe. We also have screening mechanisms that can come with these theories. So this means that we recover the solar system. I mean, yeah, inside some region, the effect. I mean, we recover general relativity, roughly speaking. And also, what was interesting in this theory is that there were this general belief that the most general relevant scalar tensor theories were of the Horndeski types. And this is very interesting because finally, if this is true, that these theories, they provide a parametrization of consistent modifications of general relativity viewed as effective field theories at a large scale. And then we have a framework to test general relativity at these scales. And this is very, very exciting and very, very interesting. But this is not the end of the story, as in fact, when we rediscovered this Horndeski series, we realized a few years after that, in fact, many theories which are physically viable in the sense that there are scalar tensor, 2 gravitons and 1 scalar. We discovered new theories which do not belong to the Horndeski class. And maybe you heard about these theories. They were called beyond Horndeski, or GLPV, for Glaise, Langlois, Piazza, Vernizzi. Also, there were this mimetic theory and new theories called custom. A lot of funny names appeared. And many of these theories, they just do not belong to the Horndeski class. So we find a lot of things. There were many theories that we didn't, I mean, there were a need to classify all of them. And now comes the DHOST classification, because the aim of the DHOST classification was exactly to classify all what was known and to see whether it was possible to construct new theories or not. So I'm not going to enter into the details because time is running. And just a few words about DHOST theories. So DHOST means degenerate higher order scalar tensor theories. And these theories, in fact, to date, they provide the most general viable scalar tensor theories where the Lagrangian contain up to second derivatives of the scalar field. The equation of motions, the Euler-Lagrange equations of these theories, they are not necessarily second order, but what is sure is that we have at most one scalar which propagates in addition of the 2 graviton. So this is interesting. And now we know that these DHOST theories, they encompass all what we knew before. So the beyond Horndeski, the Horndeski, and also the green part, which are the usual, the traditional scalar tensor theories. So I'd like to, I don't know how much time I have, maybe.
11 minutes.
11 minutes, so I will try to be quick. I like, before going to the phenomenology, I'd like to tell you what is the idea behind the construction of those theories. So as I told you, what we did here is constructed the theories with second derivative of the scalar field in the Lagrangian to mimic what happened with the DGP model. And we know that because the phenomenology and the application to cosmology will be really interesting. So to understand what is the problem with having higher order derivatives, I will give you just a toy model, very simple one. And we consider a point particle, phi of t, and assume that you have this kind of action here. So you see here, you recognize the usual harmonic oscillator, and you add this phi double dot square in the action, which is unusual. If you look at the equation of motion that you derive simply from this action, you get the harmonic oscillator plus a phi 4 dots for the derivative of phi in the equation of motion, which means that, of course, you need 4 initial conditions to integrate this equation, and 4 initial conditions means that you have 2 particles which are propagating in the theory. So what's wrong with that? What is wrong is that there is this Horndeski theorem which says you that in this kind of series, in fact, this new degree of freedom is problematic. There is a very simple way to see that. The simplest way is the following. Instead of considering this action, you can consider this one, which is strictly equivalent. So if you look at this action and look at these equations, you recover exactly, I mean, this Lagrangian is equivalent to this one. And if you take this Lagrangian, you see that you can just concentrate on the kinetic terms. So you have here a kinetic term to the square minus a kinetic term to the square, which means that if one has the right sign for the kinetic energy, the other one has necessarily the wrong sign. So this is a sign of an instability. There is an instability in the theory, and this is the well-known and the celebrated Horndeski instability. So if you have 1 degree of freedom with higher derivative in the action, you have this instability and you cannot escape the instability. But what happens that if you have now 2 particles propagating in the theory, phi and q. So again, you consider the same action as the previous one. So this one, we know that it has an instability, but now you add a new harmonic oscillator like this one, and a coupling between phi and q. If you write now the equations of motion, they are not complicated to find, trivial to find, but you see that the structure is quite complicated because here you have the 4th derivative of phi, here 3rd derivative of phi, 3rd derivative of q, and it's not easy to guess how many degrees of freedom you will have in this theory. And in general, it's not easy to guess, but you have 3 degrees of freedom that are propagating, 1 for phi, the original variable phi, 1 for q, so the second harmonic oscillator, and 1 ghost. The extra degrees of freedom will be a ghost, and you can show that you have a ghost. But in some cases, in fact, when you have a coupling between 2 degrees of freedom, you can evade the Horndeski instability. And this example is particularly interesting for that because you can show very easily that this action can be reformulated exactly like this one. So this means that instead of working with small q, you work with capital Q, defined like this, then this action here is totally fine. There is no higher order derivative, and there is no ghost in the series. So the lesson that we can take from this example is that when you have second derivatives in the action, if you have a coupling between 2 types of particles, then you can evade the Horndeski instability and have a safe theory. And this is exactly what we did in scalar tensor theories, because in scalar tensor theories, you have the tensor, the scalar, that are coupled, and you can find the coupling in such a way that you evade the Horndeski instability. And this is the main tool to construct those theories and to construct the most general scalar tensor theories that is physically viable. So what we obtain at the end of the day, if we go back to scalar tensor theories, is this kind of action here, where you have the Ricci scalar, so the usual Ricci scalar that you have in general relativity, and the scalar fields phi that comes in a rather funny way. So here you have the K-sense term, the box phi, the cubic Galilean, and then you can add you can see second derivative of the scalar field in that form, phi mu, box phi square, and other combinations of quadratic of terms that contain quadratic, and other combination of that type. And we can show that here we have a lot of free functions, so G2, G3, G4, and the function AI. But we can show that this function AI, they are not independent. And we have many functions, but there are a lot of relations between these functions. And at the end of the day, the theory, the quadratic part, contains only 3 free functions. So I don't want to say more about this construction, but just to say that those theories can be constructed in a very systematic way, and there is a clear parametrization of these theories. So now let me just quickly go back to give some cosmological applications, and maybe if I have time, I will also tell you about astrophysical applications, and I will discuss to finish the famous constraints on gravitational waves, on the speed of gravitational waves. So why we constructed those theories? So the idea is to have models to get alternative to explain the acceleration of the expansion of the universe. So we start with this DHOST theory, and then you can try to see whether you can have a phase where you have the acceleration of the expansion of the universe at a late time. So this is possible, and this is not the most complicated thing that can be done. So indeed, you can consider a background in this theory, which is a cosmological background. You assume homogeneity and isotropy, and it is possible to have self-acceleration. This self-acceleration mimics what we have today, but of course, the equation of states will be different than the equation of states of a cosmological constant here. So the background is fine. Then what is really important is to look at the perturbations, so the cosmological perturbations about this background. Looking at the perturbations is important for many reasons. First of all, to study the stability of the solution, and also to make contact with experiments and with observations. So now, as we have 2 types of degrees of freedom, 1 scalar and the 2 gravitons, we have 2 types of perturbations, zeta and gamma. And if you look at the action, the DHOST action, and you make, you look at the perturbation about this action, after a long calculation, but after the calculation, you get that the quadratic action for the perturbations is given by the sum of an action for the scalar perturbation, like this, and an action for the tensor perturbation, like this one. Here we see that the scalar perturbation propagates at a sound speed cs that you can obtain immediately from, you can get the expression of cs in terms of the coefficients of the DHOST theories. And here also you have the speed ct of the gravitational waves in these theories. One important consequence is that the tensor modes here, they do not propagate at the speed of light in general. And in fact, you can compute ct square in terms of the functions entering in the DHOST theories, and they are given by, ct square is given by this formula. So you see, you have something which is not 1, obviously. The reason why you have ct different from 1 is that physically, the gravitational waves, they propagate in a medium, which is made by this dark energy. And in the medium, the speed of the gravitational waves is modified. In a sense, the gravitational waves, they fill the fifth source. And this makes the speed of gravitational waves different from 1. And you all heard about these events GW 1708-17, because the neutron star mergers, and we had a very strong constraint on the speed of the gravitational waves. And we found that, the gravitons, they propagate at the speed of light up to this fraction, which is, of course, extremely small. And so there were a lot of discussions about this constraint. And if we take strictly and seriously this constraint, if we say that, okay, ct is 1, then we have very severe constraints on DHOST actions. And we must take, here you see, A1, one of the coefficients, to be 0, because if A1 is 0, then CT square is 1, so we are fine. A1 0 means that Horndeski theory are ruled out, will be ruled out by these constraints. And also there were a lot of studies about, I mean, a lot of other consequences on of this event on DHOST theories, and it was shown that not only A1 will be 0, but most of the coefficients in the action will vanish for some other reasons that I don't have time to explain in detail. But I'd like
Karim, the regular time is up, so you might want to decide what you still want to mention and whatnot.
Okay, let me just finish. Yes, with one side, because this is important just to finish with that. Is that so? It is important to say that those theories, there are effective field theory, so they have a domain of validity, and the scale where the tensor scale of the theory is 300 Hz, and the LIGO wavelengths, I mean the wavelengths of the gravitational waves that we measure with this event was exactly, I mean, was in the wavelength was typically at the order of 100 Hz. So when we look at the gravitational waves from LIGO and Virgo, then we are really probing the theory exactly at the domain, I mean, at the frontier, at the limit of the domain of validity. So it's not clear that there's all this, that to say that we have to be careful with the constraint that we use to eliminate the DHOST theories. So as I am running out of time, I will stop here. So sorry for being late.
Thank you very much. There's a question by Ian O'Corgan.
Yeah, okay. Thanks, Karim, for the nice talk. So to put this talk together with Licia's talk, right, we know that like local H0 seems to be biased higher than Planck lambda CDM. Okay, and so some simple way of understanding this is to look at the equation of state for dark energy. And roughly if W goes above -1, then you expect H0 to go down. And if it goes lower, you know, goes lower than -1, then H0 should go up. So in principle, you can also use this. I mean, it's just a rule of thumb, but you could also apply these to these DHOST models. And you should probably be able to eliminate 40 or 50% for them, in addition to the gravitational wave constraints. So myself and Shaheen and Lavinia Heisenberg, we basically proved that in quintessence, which I guess is one of the very simplest models here, that basically H0 always has to go down relative to lambda. So if you deviate away from the cosmological constant, then you exacerbate Hubble tension. And I think it's an interesting thing. I'd be interested to get your view.
Okay, thank you very much for the comment. Yeah, I'm aware of many different modified theory of gravity that try to decrease the Hubble tension. And myself, I also worked a bit on not a DHOST theory, but what is called minimally modified theories of gravity with the group of Kyoto around Shinji Mukuyama and others, and we show that in some cases with some models it is possible to reduce just a bit the Hubble tension. But I agree that yeah, probably there are many other possibilities to constrain these theories when we take them as models or as alternative for dark energy.
Okay, there's another question by Zakaria Belkhadria.
So thank you very much for the talk. I have just two simple questions. The first one about constraints that eliminate all the coefficients. Are they the constraints coming from cosmology, or the one that is about gravitational waves decay? Yeah. And the second one, if we obtain other solutions by disformant transformations between when we jump between beyond Horndeski, between Horndeski and DHOST, and between solutions in DHOST by disformant transformation, it's valid only for vacuum. So how it's important knowing that everything is full with matter?
I'm sorry, but I have problem. I mean, I didn't completely hear what the question. So the first question.
Okay. Yeah, the first was about the remaining coefficients that was eliminated. Was it by cosmological data or the precise constraint coming from gravitational wave decay?
Yes, you're right.
The second one is about this formal transformation. It's only valid for vacuum. That's right. So how we can consider them important to jump between solutions in DHOST or between Horndeski and DHOST if we are working, if we need only vacuum, but in reality, we know that everything is full of matter.
Okay, so concerning the first question, you're right. In this slide here, I've just taken into account the constraint on the speed of gravity waves, and I agree with you. And I try to say that when you take into account also the gravitational wave decay due to the Cherenkov effect, then you eliminate more coefficients in the actions. But I didn't have time to discuss this, and this was studied by these people here. You see, Karim, Lewandowski, Tambalo, Vernizzi in a very nice, in a series of papers. Concerning the disformal transformations, I don't really understand the question because the thing is that in this DHOST, there is one class, the physically viable class of DHOST theories is disformally related to Horndeski. This is true, and this means that all those theories are equivalent to Horndeski in vacuum, which is true. But when we have a coupling to external matter, dark matter, or anything, or photon, or lights, or anything, or radiation, then theories are inequivalent. But this is totally fine. There is nothing problematic with that. But maybe I didn't understand very well the question.
Because I thought if we found solutions like some cosmological solutions in Horndeski, and we want to get their transformation, this form of transformation, into DHOST, it will be a problem if this transformation is only valid for vacuum solutions.
No. You can have disformal transformations, even though you don't have. If you consider those theories coupled to external matter, it's totally fine to have a disformal transformation. The only thing is that a DHOST theory plus matter, which is minimally coupled, is not equivalent to Horndeski, minimally coupled to matter. That's it.
Okay.
From these kind of transformations.
Okay. Thank you very much.
Okay, let's thank Karim for a very nice talk. And then we can